Hello, hello. Alrighty. Uh, so from the gameplay video, we extract the frames. And once we've extracted all the frames, our first step is to recognize all the sprites that are available in this video. The way we do this is through a sprite extraction network. In our case, we use Marionette, which is a self-supervised sprite learning architecture. And what this does is that it learns a sprite dictionary from the video, and it also converts the frames into a grid. Like here you can see that the grid has 5, 5, 5, and if you look at the fifth index, that's blank, right? Or here you could see 3, and 3 means a pellet, right? So it's essentially converting all the frames into a grid. Once you've converted all the frames into grids, we need to learn the actual behavior. How do we do that? Let's take this example, right? We have frame I and we have frame I plus 1. You could see that the Pac-Man is going towards the pellet, and when the Pac-Man reaches the pellet, then our Blinky turns into a ghost. So a potential code for this could be that if Pac-Man and pellet collides, then Blinky changes into ghost, right? So we need to learn this. So what we're going to do is for each of the sprites that we learned in our dictionary, we're going to learn a unique program. And all of these programs are going to be if statements. So they're going to have a condition and they're going to have some action. We're not going to learn anything for Pac-Man because the player is controlling Pac-Man, so that's not really required. So we defined our own DSL for this to narrow down the space called retrocoder, and here are the conditions that we defined. One condition is whether an entity exists in map. For example, here you could see that Pac-Man exists in map, whether an entity neighbors some other entity, in this case, Blinky neighbors Pac-Man, or whether two other entities neighbor each other. In this case, Pac-Man neighbors a pellet. Similarly, we also defined some actions. One is follow entity, in which one entity has to follow another entity. In this case, Blinky is following Pac-Man. We have follow direction, in which case Blinky is following a direction, in this case, west or east, west. You have change to entity, in which case Blinky changes into a ghost or anything, right? Any entity can change into some other entity from the dictionary. And finally, follow some random location. So what we did was using all these functions, we performed a search that matched the next frame for each of the frames. And what were the results? Here is what we were able to produce, right? So we are controlling Pac-Man here, and we could see that Blinky did learn to follow Pac-Man. And as soon as Pac-Man collided with a pellet, Blinky transformed into a ghost. If we dive into the actual code, we can see that for Blinky, as I said, if Pac-Man exists, which it always does, then Blinky follows Pac-Man. And if Pac-Man is neighboring with Power Pellet, which is a collision, then it changes into a ghost. Similarly, for the Power Pellet, if it's neighboring with Pac-Man, then it changes into Pac-Man. This might sound weird. The reason it does that is because Pac-Man occupies its position. So on the grid cell, Pac-Man takes its position. Unfortunately, the code that we learned in the middle for all the eyes and the ghost sprite is not coherent, and it doesn't really do anything for us. And the reason why we ran into this issue was that Marionette was doing some hallucinations where sometimes it would return grids that were not true. For example, here it thought that it had two blinkies instead of one blinky, right? So our representations were not 100% accurate. We also compared our approach to two baselines. GameGAN is a neural world model, and game engine learning is a symbolic world model that Matthew did about 7, 8 years ago. Do note that for GameGAN, we use the same video that we did for our approach, so the training data is very minimal, right? And as a result, GameGAN didn't perform well at all. We use this metric called FID, which is commonly used to measure the flow in videos. And for GameGAN, the results are very poor because it was just returning the same frame again and again, and it wasn't coherent at all. Our results are quite comparable to game engine learning, as you can see. Similarly, for the MSc loss, our results are quite comparable. And again, GameGAN is doing quite poorly. In terms of conditions, you can see that our approach has fewer conditions than game engine learning. That's because game engine learning has a top-down approach, whereas we have a bottom-up approach. So the conditions that we're learning are more generalizable, which is a good thing. In terms of future work, one thing that we definitely need to work on is a better representation, right? Marionette, it's a good starting point, but it would be good if we can work on the hallucinations. We could also expand our DSL to have more functions, to generalize more. And it would also be cool to do this with 3D games, right? We would need a 3D representation for that. You could try something with occupancy grids, which could be cool. And yeah, here's my LinkedIn and Blue Sky if you want to connect with me. I'm also working on this small indie game. It's on Steam if you know wishlist it. And yeah, questions.
Fantastic talk. And yes, let's make sure you post a link to that game in Discord.
It's on your spreadsheet. Sure. So we are learning code that's across the video, right? We're not learning things that are memory dependent. We are learning stuff. It scans like the entire video and then it learns conditions that are true across the video. So as long as something happens in the video, and that's true, then it should be detected by the search. Does that make sense? Did I answer your question? Okay. Yep. Sure. Any particular one or all of them? Sure. So FID is a Frechet inception distance, right? And it basically measures the flow, how a video flows. For diffusion model, it's a common metric that's used. The reason it's bad for GameGAN is because it's literally the same frame repeating again and again and again. So there's literally no flow at all. Yeah, for sure. Something that I didn't touch on is that the game engine learning, what ended up happening was that the code that game engine learning learned, it wasn't having any effect on the frame. So the frame was essentially the baseline frame, which is close to the player. So the game engine learning is very close to what you suggested.
I was wondering, I was really intrigued by this thing that you don't try and predict the player or create code for the player, which makes sense. Does that mean you can tell your system that the player is blinky, that Pac-Man is controlled by the AI, and then just kind of see what it comes up with, like some kind of broken art game?
Yes, you could try that. I haven't tried that, but you certainly could. I don't think it's going to learn anything coherent for Pac-Man because it is just random directions, right? Unless the player is very systematic and they're following some pathfinding algorithm, maybe. I'm pretty bad at it, but yeah, perhaps. Um, So we didn't compare against the programming synthesis techniques. What we did was we did have different approaches to programming synthesis, right? Where initially we tried a brute search, but it was quite slow. And so we just tried, optimizing our algorithm to make it quicker and quicker. We didn't have any benchmarks against something like Dreamcoder or anything, but it was more so whatever worked best because it is a bit specialized. No questions?
I think we'll call that then. Thank you so much.